Bootstrap for BPS black holes.
Thank you, and first of all, thanks to organizers for bringing us to this wonderful place. I'd like to present here results of a series of works which I did with my collaborators, Boris Pulin, Nava Gadam, Jan Manshot, Sohail Fisbach, Albert Klem, Torsten Shimaniak, and also work which I'm finishing now with my PhD student Khalil bin Riz. So the talk will be about computing of BPS indices in Calabi-Yau complications of string theory. So first, let me start by explaining precisely the subject of the talk and just give the main message. So let's consider the following setup. Just type 2A string theory compactified in a Calabi-Yau threefold. Well, it's well known that in 4 dimensions, then we find n equal to supergravity, which is coupled to some number of hypermultiplets, vector multiplets. And in this theory, we can define BPS indices, which count with sign the number of BPS states. And they are labeled by electromagnetic charge, which is a vector with two B2 plus 2 components, where B2 is the second Betti number of the Calabi-Yau, just because we have B2 plus 1 gauge fields. B2 of them come from vector multiplets, and one additional one is a graviphoton. And so let me label in the following my charge vector as follows. So where A runs from 1 to B2, and here P's will denote magnetic components of the electromagnetic charge, and Q I consider like electric components. And these BPS indices, they have incarnations both in physics and mathematics. Namely, in physics, they count the number of half BPS black holes, which in this setup arise as bound states of D6, D4, D2, D0 branes, wrapped on respectively 6, 4, 2, 0 dimensional cycles of the Calabi-Yau. And this is why this decomposition of the charge is convenient, because here we precisely have association of these components with these D6, D4, D2, D0 brane charges. Namely, for example, P0 gives the number of D6 branes wrapped on the whole Calabi-Yau, and so on. And in mathematics, this BPS index is nothing else but the so-called generalized Donaldson-Thomas invariant of the Calabi-Yau. And probably in this audience, I shouldn't explain why it's important to compute these BPS indices. But let me nevertheless mention that for non-compact Calabi-Yaus, there are many techniques. Some of them we heard during this program. How to compute these BPS indices using localization, queries, or something else. But most of them just do not work for compact Calabi-Yaus. And it's a tremendous problem how to compute these guys for compact Calabi-Yaus. And this is what I would like to do here. Actually, my main point of interest will be not arbitrary DT invariants, but the so-called rank 0 DT invariants, which correspond to vanishing D6 brane charge. So P0 will be equal to 0 in the following. And then we consider the so-called D4, D2, D0 bound states. And due to certain symmetry, it's nice that these BPS indices, well, the dependence on D2 brane charge can be almost removed. Not completely, because we still have certain residue class, which takes just finite number of values, namely determinant of this particular quadratic form, which is constructed from intersection numbers of the Calabi-Yau and D4 brane charge. So in the end, our BPS index is labeled by D4 brane charge, this residue class, which takes finite number of values, and certain modification of D0 brane charge. Just it's convenient to do it because this guy stays invariant under the spectral flow symmetry. And once we have this labeling, we can form the generating function. Yeah. Well, I don't know. Well, to be fair, I don't know precisely how this So what these generalized DT invariants do? What? Well, yeah. Uh, well, then I reduce to just Dino zero go Pakumar Waffe invariant. Because no, if I say if I take, as you said, vanishing D4 branch charge. So no D4, no D6. Then it's just D2, D0, and it's known that DT invariance for those guys reproduces Dino zero go Pakumar Waffe invariance. No, the other genera, they appear, for example, if you add D6, they will appear. But for if there are no magnetic charges, it's just Dino zero go Pakumar Waffe. These are those guys which enter in the holomorphic prepotential of topological string.
What is slightly confusing is that when you remove the D6, you are not doing wall crossing to PT chamber or stuff like that.
I will do later. No, these guys secretly know about GV invariance of all genera. Yeah. Say it again. The end. No, wait. Because you're, no. Here, my D4 branch charge is non-vanishing. Then there is this reduction. Then the symmetry allows to reduce to this finite number of values of D2 branch charge. Otherwise, it's not true. No. Yeah. For example, if I consider a D6 branch charge non-vanishing, then this guy would allow us to do the same reduction for D4 branch charge. Yeah. Okay. So let's continue. So, yeah. Well, yeah, you can say mathematically, this spherical flow is tensoring with the line bundle, if these words help you. So let's form this generating function, and we can do this because this Q0 hat is bounded from above. This is the so-called Bogomolov bound in mathematics. And of course, it's much more convenient to work with this generating function. And there is an important comment that actually to form it, to have nice properties of this generating function, you should consider the rational version of these guys, not the integer one. And the message is that this guy has nice modular properties. I will explain you later precisely what these modular properties are. Just let's make me this point here. And kind of the main message of my talk is that we developed a certain procedure how to compute, well, an infinite number of topological invariants related to the Calabi-Yau following, well, this procedure which I depicted here and which I'll explain more during my talk. But roughly speaking, you start from GV invariants which can be computed by solving topological string theory, for example, by direct integration method. Then you apply the so-called MNOP formula to get PT invariants. Then you do certain wall crossing to get a few these rank 0 DT invariants, but then using modularity, you can actually find the whole generating functions. And once you know them, so you know infinite number of these guys, and now you can actually go even back and find new PT, new GVs, and so on. I'll show you, but roughly speaking, so I can tell you we dealt with one parameter Calabi-Yau, and for the unit D4 charge, we managed to find generating functions for 11 of these guys, 11 Calabi-Yaus. So we worked with complete intersection Calabi-Yaus with one Keller modulus. So there are 13 such Calabi-Yaus, so we managed to do with 11. One example, quintic, for example. Yeah, you will see later. So this is the plan of my talk. So first I'll describe the most trivial situation precisely with the unit D4 brane charge, or in other words, where the divisor rubbed by D4 brane is irreducible. I'll explain what happens with the wall crossing here, how it can be applied, MNOP formula, and then present the results. Then I will move on to more interesting cases where there is actually a modular anomaly. So I'll explain how it arises, how it can be solved, and how one can obtain explicit results. And then finally, I would like to tell you about some work in progress where I consider it in even the so-called high depth case, and where we essentially solved this modular anomaly. Yes, yeah. In on-compact case, it's yeah, essentially the procedure is the same. It's even easy in that case, yeah. Okay, so let's start from the most simple case of reducible divisors. Namely, we have D4 brane wrapped on some 4 cycle, which is supposed to be reducible. So you cannot decompose it as a sum of other 4 cycles. And then the claim, which is very old, you see like 25 years old, is that this generating function is weakly holomorphic vector valued modular form of this particular weight determined by the second Betti number. So here I just remind you what these words mean. So weakly holomorphic means that if you do Laurent expansion, then there are powers of Q, which is just exponential of 2 pi tau, as usual. There are negative powers of Q in this series. That's important. And vector valued modular just means that it transforms in the standard way under the SL to Z transformations. And vector valuedness means that in this transformation, you can have the so-called multiplier system. So certain matrix, which is typically just given by some phase factors. So it's known, it's very simple. Yeah. D2, you remember D2 charge was reduced to a finite number of values, yeah? Yeah, I fix it, and this is my vector index. This is why I say that this is a vector valued model form. Yes, yeah. And this claim actually comes from a certain physical argument that you take M5 brane, wrap it on a 4 cycle, you get certain superconformal field theory, compute elliptic genus, and then you find this generating function in the so-called theta series decomposition of this elliptic genus. Since elliptic genus should be modular, theta series is also modular, so therefore this guy should also be modular. Then how do we proceed? Well, there is a beautiful fact that the space of such weakly holomorphic modular forms of fixed weight is finite dimensional, and moreover, the dimension is bounded from above by the number of polar terms, where by polar terms I mean terms with the negative power of Q. So which means it's just enough to compute these guys, the coefficients of these polar terms, and you are done. You can completely fix the generating function. So you can expand it in some fixed basis, for example, of some theta series, and you are done. So you get it explicitly. And this is precisely how we address this problem for what I already mentioned. So complete intersections Calabi-Yaus with one Keller modulus, and there are 13 such guys. Actually, 5 such Calabi-Yaus have been already considered in the literature, but using different techniques, and even the results for some of them were controversial. So there were some disagreements about what is the right generating function. And I believe we fixed all these problems. So how do we proceed? Well, the main point is to use wall crossing. probably most of you know this very well, but let me remind you that wall crossing just means that these guys are piecewise constant in the modular space, and it arises because these BPS indices count not only single-centered black holes, but also their bound states. And you know the bound state can be stable in one region of the modular space and unstable in the other region. So the whole modular space is divided into chambers, and omega takes different values in these chambers. In this context, the positions of the worlds is determined by the central charge, which is just linear combination of charges, and it will be important for the following that the coefficients of Q lambda are just my Keller moduli, and coefficients of magnetic charges are first derivatives of this holomorphic prepotentials, which governs the geometry of the modulus of the Keller modular space of the Calabi-Yau. Yeah, this is just Gino 0. And at this point, you could actually ask me, but wait, since my omegas are different in all chambers, so which guys you compute? Which omegas? In which chamber? So in my talk, if it's not specified otherwise, I always compute my omegas in the so-called large volume attractor chamber. So it means that I fix my model in terms of the charge vector, and so I put here certain coefficients and scale it to infinity in the end. So this is large volume limit. And the important fact is that we actually know how to cross walls. Namely, if we know omegas in one region of the modular space, we can compute it in the other region using certain universal wall crossing formulas due to Kontsevich-Soibelman or Joy-Song. So they apply everywhere. So at least in principle, we can do this. And this means that it's enough to compute the BPS indices in just one particular chamber, and then at least in principle, we should be able to move into the chamber which we're really interested in. And this gives the following idea. So let's find our BPS indices. Let's find a chamber where the BPS spectrum is simple. And then compute there and move to our chamber, large volume chamber. But the problem, and this is a strategy which is sometimes used in supersymmetric gauge theories, but the problem is that in supergravity there is no chamber with a simple BPS spectrum. That's a huge problem. And this is what differs the compact case from non-compact one, maybe. But here mathematicians come to rescue, actually, because they suggest to do something which is completely unphysical, but mathematically makes sense, perfect sense. So what is this? You should remember that these BPS indices, you remember, they count stable BPS states, so they define by the so-called stability condition, which in our case, it's controlled by this central charge function. Yeah? And as I told you, the coefficients here are Z lambda and F lambda is a fixed function of Zs. Yeah? It's our holomorphic prepotential. But from the mathematical point of view, there is no obligation to take these F lambdas to be functions of Z. You can take them to be completely independent. And then we start exploring what is called the space of stability conditions of the Calabi-Yau. So it's some big space where the physical slice corresponding to this stability condition, well, is just some slice. Yeah. But you can consider other slices as well. And in particular, there is one nice slice, which is called the so-called new BW stability, which lies somewhere at the boundary of this space of stability conditions. And it turns out that with respect to this stability condition, there is a chamber where many BPS indices actually vanish. And moreover, in the large volume region, this stability condition does not essentially differ from the physical one. So if you count with respect to one stability condition BPS states, they will give us the physical number. Sorry? Yeah, sure. But it's important that some of them can be zero. And then this gives us the idea. Let's start in this chamber, for example, from something which is zero, and move on to this large volume and just compute what we get in the end. Yeah. Well, yeah. What is the meaning of what? Uh, well, for one parameter, at least for one parameter Calabi hours, some you see here there is some huge territory unexplored, but some subset of all possible maybe stability conditions have been rigorously constructed by mathematicians. I forgot the names, Maki, yeah. And inside this space, there is a physical slice, which is well defined also. So you can just compute, there are explicit formulas. So at least this corner, yeah, is mathematically well defined, yeah. Yeah, and one more? I'm not sure, because in non-compact there are already chambers with the simple spectrum, so there is no need for that probably. Yeah. And just to finish this slide, precisely this idea, going from here to here, was followed by Sohaila Feisbach, who derived an explicit formula relating rank 1 and rank 0 DT invariants. And on the next slide, I'm supposed to explain you how this formula looks like, at least schematically. So you start from certain imposing conditions on, well, essentially D2 and D0 brane charges, which is needed to ensure that our starting BPS index actually vanishes in that chamber, and also that on the way from that chamber to the physical one, we encounter only walls with one D4 brane. So this condition ensures that. And then our PT invariant with these charges is just given by, well, essentially iterative, it's a result of iterative applying this primitive wall crossing formula. So chi here is this Dirac product gamma 1, gamma 2, and you see there are two BPS indices. One is another PT invariant, which is, by the way, I forgot to say that PT invariant is just DT invariant with of rank -1, so with the D6 brane charge -1. And here you have our D4, D2, D0 BPS index. And the idea is that D4 brane charge here cancels D4 flux on anti-D6 brane here. Yeah? Just D2 and D0, if you wish. Yeah, D2 and D0. Well, some shifted version of them. Yeah. It's even easy. It's a primitive wall crossing formula, just applied several times. You just yeah, the real content of this formula is what I didn't show you, is the range of summation over Q prime and M prime. So what Sohaila did, she found all the walls which you encounter on the way and just took them into account and wrote this formula. And for this, one should work very carefully, of course, yeah. And here I didn't show you these precise ranges of summation, but there are two important consequences of these ranges. The first of all is that Q prime is always less than Q, which means that this formula is recursive. So knowing invariance with low charges, you compute invariance with higher charges, yeah? And another important consequence is that there is always a contribution with Q prime and prime equals 0, which has PT invariant equal to 1, so that we always have a term which is just D4, D2, D0 BPS index. And then what we can do, we just put it on the left-hand side, this guy on the right-hand side, and as a result, we get an explicit formula expressing rank 0 DT invariant in terms of other invariants. So here, PT invariants are actually defined as invariants at the large volume, but the idea is that you start from that chamber with respect to this non-physical stability condition, you start from 0, and then you go to the large volume chamber where the okay, if you wish, you can go in different way. Just start from the large volume where you define this PT invariant and go to that chamber where it vanishes. So it's known that this guy, if the charges satisfy certain condition, it will vanish. Yeah. Yeah. Yeah, because you know, indeed, when you move, you kind of go out of your large volume chamber. So therefore, you may think that on the way you will encounter invariants in those chambers, but actually you can show that those invariants, they are the same as in the large volume. So this can be shown. This is not strict, true will be for more general formula, but for this one it's true. So one can show this. Yes. Yes. I will show you. I will show. Yeah. But for example, for quintic, as I said, yeah. Hmm? Well, we do know. We computed them. You will see. Just wait a bit. Well, because in that picture, well, unphysical because in the stability condition, f lambda is not the derivative of the physical prepotential. Well, you can call it maybe not physical. I mean, the standard one, prepotential of which describes scalar model of the Calabi-Yau, but it's some other function, which is supposed to describe this particular stability condition. So it's just a different function, which you don't see in physics. This is why I call it non-physical. Okay, just one last comment is that actually you could think that this formula will be valid only for these particular charges. I mean, the formula expressing rank 0 dt in terms of the others, but actually it works for any d4, d2, d0 charge because you can use spectral flow invariance to all this, which does not change the BPS index, but it changes the charges, and applying this formula, you can always satisfy the required inequality. Therefore, the final formula valid for any d4, d2, d0 brane charge. But now the question is how you compute this PT invariants. Well, using MNOP formula, which expresses them through GV invariance. So this is some standard mathematical result. So let me very briefly to recall it. So we have a topological string partition function in a Gopakumar-Waffe representation, which is expressed in terms of GV invariance of all genera, as you see. And on the other hand, we can introduce generating function of PT invariance. And Maulik, Nekrasov, Okunkov, Podkhrypan proved that these two functions are related in the following way. Well, I think by now it's proven. This is what I heard. What? Yeah. Okay, yeah, they conjectured and some others proven. Yes, sorry, yeah, and and even before the proof was done, well, at least all physicists believed that this should be true. And you can use this formula to compute these guys. So you just expand both sides, and either you get PTs in terms of GVs, so it works in the other direction. Also, you can compute GVs in terms of PTs. And well, now you can ask, but okay, how I compute GV? Well, I just solve my topological string theory. For example, using direct integration. I use the fact that this guy satisfies certain holomorphic anomaly equation, solve this holomorphic anomaly, and in this way get my topological string partition function. The only problem is that, well, as you can guess, this is holomorphic anomaly equation, so it gives its solution has a holomorphic anomaly. Holomorphic ambiguity, sorry. So you can add any holomorphic function, it will still be a solution. So therefore, to fix it, you need to impose a kind of boundary conditions. And the problem is that the number of known boundary conditions grows slower than the number of parameters on which this holomorphic ambiguity can depend. And as a result, there is a maximal genus where this method just stops. It doesn't work anymore, just because you cannot fix the holomorphic ambiguity completely. That's the fact of life. But nevertheless, up to some maximal genus, it perfectly works. And now, so let me just present the results in this context. So what we have done. So I told you we took our completed intersections one parameter Calabi-Yau's. We kind of improved numerically this direct integration method to actually reach this maximal computable genus for most of these Calabi-Yau's. And this allowed us to compute sufficient number of these PT invariants to get all polar terms in our in the expansion of the generating functions of rank 0 DT invariants. Well, not for all Calabi-Yau's, but as I said, for 11 out of 13. And since we know the polar terms, we can fix out generating functions completely, so some vector valued modular forms. And in fact, we can do even better because we can compute also some non-polar terms and compare these terms with the expansion of the modular functions which we obtained from its duality, from this modularity, and they perfectly match. So it's really amazing to see how some, I don't know, huge numbers with 30 digits, they match, they are computed by completely different methods, and it works. So this proves that the whole machinery is reasonable. And now you can do even better, so you can expand the generating function up to arbitrary order. In this way, you get infinitely many rank 0 DT invariants. And now you can actually go back. You can use them to actually find PT invariants using that wall crossing formula which I showed, and then using the MNOP you can compute new GV invariants, and these guys will serve as a new boundary conditions for the direct integration method. So you can actually bypass the limitations of the direct integration method. For example, for quintic, the direct integration works up to genus 53, but we already achieved genus 64. No, sure. This is what I'm saying, that once you know polar terms, you can compute generating function, and you derive all terms. But then you can also compute those terms using that wall crossing formula. No, unfortunately, no, it doesn't work. How to explain it? No, it does not work like this because when you how to say it? When you compute this rank 0 DT invariants and you apply this wall crossing formula, so how to say it? You do not get all kind of invariance for all charges like one by one, yeah? You kind of jump, you find GV, some PT invariant of, I don't know, 1 D0 charge, then this D0 charge plus, I don't know, 3, plus 6, and so on. So there are gaps in your knowledge. And sometimes it's possible to fill these gaps, sometimes it's not possible. No, just well, no. It's I don't know how to explain it. It's just how equations work, and it's yeah, but it's just that yeah, you can see that yeah, all these guys, even if you know infinitely many of them, are not enough to compute PT invariance for all charges. There will be gaps in your knowledge. So that's the claim. Yeah. All D6 even? No, then you know everything. Yeah. No, but still, to get GV invariance, it's enough to know just for DT invariance for or PT invariance for D6 branch equal 1. So I don't need to know others. But still, I don't know even those because I will have gaps in my knowledge. Should I continue? Okay, then I want to consider something more interesting, because this was just about the usual modularity. Essentially, we just improved how to compute these polar terms for unit D4 branch charge, but now really something new. So I'd like to consider the cases where my divisor, route by D4 brane, is reducible. So for example, in the context of one parameter Calabi hours, it means that my D4 brane charge is not equal to 1, but equal to 2, 3, 4, any value. And then the claim is that my generating function is not modular function anymore. It does have a modular anomaly, but of very specific type. Namely, this anomaly is such that this particular combination of generating functions, you see, for various charges, so Pi is my D4 brane charge, that this guy, which we call modular completion, transforms as a true modular form of the same weight. So this is the claim. Of course, to make sense of this equation, I should specify for you these functions R, which appear here. Well, let me not do it explicitly, because this would take, I don't know, 15, 20 minutes to define all the ingredients. If somebody is interested, he can look at the papers. But let me just say that this is some non-holomorphic indefinite theta series with kernel constructed from the so-called generalized terra functions. If you don't know what they are, well, these are just some kind of iterative integrals of the standard terra function. And they appear in this context because they provide completions, modular completions for indefinite theta series. And also an important comment, yeah? Next slide. Next slide. Yeah. Just before that, let me say that the upper limit here in this sum is just the number of irreducible components of my divisor, and in the following I will denote it by small r. And mathematically, these results mean that my generating functions are high depth mock modular forms. So let me just very briefly remind you what it means, mock modular form. Well, mock modular form is a holomorphic function which does have a modular anomaly, but this anomaly is controlled by another modular form, which is called shadow. So you saw this type of integrals already appearing in the first talk of this day. So here they appear again. So this is Eichler integral here. And the claim is that if you take this integral, you see with the low limit tau bar, so it's non-holomorphic, and combined with the original function, you get a modular completion. So this guy transforms as a true modular form. So if it is so, then I call H mock modular. Then there is also a slight generalization, namely mixed mock modular. Then you allow your shadow to be a product, not just a modular function, but a product of holomorphic and anti-holomorphic modular forms, or sum of products. And if you want to go to higher depth, well, then you define it just recursively. So you say that your function has a depth n, mock modularity, if its shadow is a mock modular form of depth n minus 1. That's it. So in particular, depth 1 is usual mock modularity, depth 0 is usual modularity. Yeah. And now the question, why these guys should be modular? So here, so I will refer to some physics. So let me recall that we're considering type 2n in Calabi-Yau, which is the same, of course, the same theory in Calabi-Yau times a circle. And let's compactify in an additional circle. Why not? Then we go to already 3 dimensions. So we get certain effective theory in 3 dimensions. And just because all fields in 3 dimensions can be dualized to scalars, it can be written as certain nonlinear sigma model with some target space. So essentially just in the bosonic sector, it will be just bunch of scalars. So there will be kinetic term for the scalars, and it's defined by the metric on this target space M. And now you see that once we compactify in the additional circle, we have torus in the game. And of course, torus has a modular group, and this modular group should be somehow be reflected in our effective theory. And the claim is that the metric on this target space, or this target space, should carry an isometric action of SL to Z. The same conclusion you can achieve if you apply here T duality and go to the type 2b setup, and then this SL to Z is nothing else but S duality of type 2b. But now we're interested in a D4 brane wrapped on a 4 cycle. Yeah? And now we have an additional circle. So let's wrap the remaining dimension, because this guy still leaves 1 dimension, uncompactified. So let's compactify it in this additional circle. So we consider kind of Euclidean-like object. Yeah? And from the point of view of effective theory in 3 dimensions, it's kind of point-like object. And what is point-like object? It is some instanton. And the point is that these instantons, they affect the metric on this target space M. What? What is what? M. As I told you, it's some it's a modular space of this theory obtained after this compactification. But it's some it's some space with certain metric, and this metric can be computed physically. Okay, it's a quaternion Keller space, so its metric is quaternion Keller, and I can compute it like leading term corrections and so on. Set. Set is parameterized by fields in 3 dimensions, the massless fields in 3 dimensions. It comprises many fields. So there is some of them correspond to Keller moduli of my Calabi-Yau, but there are many others, like dilaton, some Ramon fields. So at classical level, you can give kind of a bundle description in terms of a bundle over the Keller moduli space of the Calabi-Yau. But once you include quantum corrections, this description in terms of vibration completely destroyed. No, global, no, not at all. Actually, it's still an open question how to compute the exact metric on this modular space. So, of course, we don't have any global description. Even locally, the complete metric is not known. Yeah, sure. Dimension is, okay, it's 4 B2 plus 4, real dimension. Okay, so what I was saying is that this metric is affected by instanton corrections, and we know that each instanton is weighted by the BPS index, which means that my metric will depend on BPS indices, which we are computing. And in fact, we know how to compute all these instantons. We found this already 15 years ago using certain twistorial construction of this space M. And just I don't have time to explain all this, but we know all this instanton corrected metric on this M, and now you see that it should carry this as a metric action. So SL to Z imposes certain restriction on my metric, And since the metric depends on omegas, it means that it imposes restrictions on omegas. And remarkably, this restriction can be extracted explicitly in terms of the generating functions of these omegas, and it precisely has the form of the equation which I showed on the previous slide. That particular combination of generating functions must transform as a true modular form. No. It includes all possible corrections with all charges. Yeah, absolutely. But it turns out that kind of all corrections can be split into, if you wish, SL to Z orbits. And you consider orbit by orbit. So, and then there is a particular orbit corresponding to fixed D4 brane charge.
I agree, but it seems like if you believe this, you know a lot more than you do.
Sorry, you. Yes, yeah. There is much more, of course. Of course. It's just one particular sector. It's a very small consequence of this huge restriction. Yeah? Yes?
For the compact RBL, after the computation of type 2A of RBL type SY, that's a three-dimensional supergravity theory. How can this be mapped to a supersymmetric nonlinear system model?
Well, the idea is that, so if you are in type 2A, so what you do, so you consider the, if you wish, vector multiplet modular space, yeah? And then when you do reduction on the circle, this vector multiplet modular space, which is special Kähler manifold, gets extended, enlarged by other fields, because all vector fields, for example, when you have vector field in 4D, yeah, after reduction on the circle gives a scalar, yeah, and another vector field. But in 3D, this vector field can be dualized to another scalar. So all these scalars now also play the role of additional coordinates on this extended modular space. And no. Yeah, there is a dilaton, for example, which also enters here. And yeah, no, sorry. If you're in type 2A, there is no dilaton because yeah, dilaton is in the hypermultiplet sector. But well, there are still fields, for example, those which come from the complication of graviphoton. Well, anyway, so I was saying that we get this equation, the completion by well, from this S duality argument. And well, this is a physical argument, and I think mathematicians do not have really understanding why these generating functions of rank 0 DT invariants must possess any modular properties. No, unfortunately it doesn't work. So if you take a generated function of rank 1 DT invariants, they will not be modular. And the reason, because D6 brane, well, physical reason, D6 brane under S duality is mapped to an S5 brane. And, well, therefore, no chance. Yeah. Well, in principle, it depends on many things, but in particular on those guys. In particular. Well, they also generate corrections, but they decouple. So they go to another SL to Z orbit, precisely the orbit which includes, for example, those with non-vanishing D6 brane charge. So it's another SL to Z orbit, and actually the idea to find this in S5 brane corrections was precisely to start from D6 and apply SL to Z. Well, again, there are many possible instanton corrections. All of them in principle should be included, but it's a mathematical fact that all these corrections kind of form different SL to Z orbits. And I'm concentrating on a particular orbit. and extract consequence of that orbit. Only D4, yeah, yes. Yeah. For example, there is another orbit which involves only D2 brain charges. Yeah, and wall sheet instantons. Yeah. Okay, so let's consider the simplest example where our divisor can be split into just two irreducible divisors, which correspond, or D4 brain charge equal to 2. So what happens in that case? In that case, our generating function is an example of mixed mock modular form of this particular weight, minus 3/2. And from that equation, the completion, I can easily derive the following holomorphic anomaly equation for this completion. So I just take this tau bar derivative. And what I find just two factors of H1, just because 1 + 1 is equal to 2. And the kernel, the coefficient here is given by certain standard theta series. And the claim that, yeah, so this is the equation which should, so this we should consider as an equation on H2. But now, if we want to apply the same ideas we had in the irreducible case, then how can we find our generating functions? Unfortunately, here it's more complicated because it's known that polar terms are not enough to fix mixed modular forms completely. You need also to consider modular anomaly. But then the idea is very simple. Let's just represent our generating function as a sum of two terms. One is an anomalous term. So, and here you can take any mock modular form which satisfies this anomaly. Of course, then generating function can still differ from that particular solution by some modular form. But this guy, then we can fix by computing polar terms. So you compute polar terms of this guy, polar terms of this guy is known, so you take the difference and you compute and you restore this function. So now we have this two-step procedure which we must follow. And the first step is actually very simple. So how you solve the modular anomaly? Well, this structure of this equation suggests the following ansatz. Then G, this capital G, should be already usual mock modular form, not mixed one. And its completion satisfies already this very simple holomorphic anomaly equation. And the nice thing is that this problem of finding mock modular forms with such shadow has been already solved in the famous paper by Murthy and Zagier when they consider black holes in N=4 supergravity. So we can just borrow solutions from their paper and we're done. And solution, of course, strongly depends on the parameter kappa, which denotes here the intersection number of my one parameter Calabi-Yau. And it's particularly simple for kappa, which is a power of a prime number. If not, it's a little bit more complicated. But what is important, so the message here is that the whole problem, once I find this solution, reduces to, again, finding the polar terms. And here again, so Hela Feisbach comes to rescue us. So she derived a generalization of the formula which I showed on the previous slide. And so the point here is to relax this condition. So now you allow walls with one or two D4 brains. And as you see, the formula is more general, so it involves now 3 terms. And what is important, there is a term where we have BPS, D4, D2, D0 BPS index with D4 brain charge equal to 2. And again, the same story repeats. So this formula is recursive, and there is a term with Q prime and prime equals 0 here, if you impose some additional condition. And as a result, you can derive an explicit formula for that guy in terms of, again, PT and the other D4, D2, D0 BPS indices. But here, precisely, we have the problem, which you mentioned, that we do not have enough PT invariance. And the reason, because, well, because we need to know GV invariance to very large genus. And unfortunately, for most of our Calabi-Yaus, yeah, we do not have enough knowledge. But fortunately, still, we can do 2 Calabi-Yaus, namely the so-called decantic and octic. And for those, we do have enough knowledge of GV invariance. And here, I just flash you the results for decantic, which is particularly simple. So here I show you, first of all, the generating function for unit deformed charge, which is just the standard modular form. It's not even vector value, just one component. So you see it's a combination of the Dedekind theta function as Eisenstein functions, so you can expand it. And here in blue, I showed the polar term. So if you know these two numbers, you can restore the whole function. That's the point. And for deformed charge equal to 2, already the situation is more complicated. So we found this explicit mock modular form. So the first two lines is just usual vector valued modular form. Now this is a two-dimensional vector because we're at charge 2. And so, well, the numbers are crazy, but just because we expanded this modular form, it's some, well, essentially random basis of some theta functions in the Eisenstein series. And what is mostly important is that there is this term which is responsible for mock modularity. And it's completely fixed by, you see, the generating function of Hurwitz class numbers, which is one of the most maybe standard mock modular forms in number theory. And you can expand it, and so given this function, you just put it on Mathematica, and you expand and get your invariance up to arbitrary charge. Okay, and maybe in the remaining 5 minutes, let me very briefly show what happens if you go to even high charges. So here I repeated this equation for the modular anomaly. Yes, default charge. So I want to consider default charge R, which is larger than 2 now, arbitrary R. And again, the idea is to use the same two-step procedure. So first, we will find some mock modular form already of non-trivial depth, which will satisfy this equation. Well, and then it's we can still have this modular ambiguity, which we're supposed to fix by computing the polar terms. Well, as you saw, computing polar terms is horribly difficult. So let me postpone this second step for future and just try to address the first problem. So can we solve at least the modular anomaly, but for arbitrary charge? And already here, there is a problem, because you see, the anomaly equation involves generating functions for lower charges on the right-hand side. And of course, those guys, they will also involve their own modular ambiguities. So my result will depend on all these ambiguities, which I didn't fix yet. Well, of course, then what it means that we can find this anomalous guy just, well, we should express it in terms of these unknown functions. And this can be done. So we just take this ansatz, introduce the so-called anomalous coefficients. Well, essentially, the formula is the same as here. So we just replace h by h zeros, this r by this small g, and that's it. So this is ansatz, and the claim now is that this restriction, this equation imposes certain restriction on this small g. And yeah, and the problem reduces to just finding these functions. So how we find them? So we derive explicitly the restriction on these guys. Again, it has the form of equation on the completion of these guys, because they, again, should be depth n minus 1 mock modular forms, where n is the number of charges, which I have here. And well, the structure of the completion, let me not go into the detail, but roughly speaking, if before you summed after all decompositions of my charge into some small charges. So now I have already n charges, and I sum over all kind of groupings of this charge. Or if you wish, I sum over trees of depth 2 with fixed number of leaves. And the claim is that we can construct a solution of this equation in terms of indefinite theta series. So what are indefinite theta series? Let me remind you. So if you consider holomorphic indefinite theta series, well, you have just the standard power of q to some q of k, where k belongs to some lattice, and q is some quadratic form, but now of non-trivial signature. So there is some number of pluses and some number of minuses. And of course, this guy is divergent. And so to make it convergent, you insert a certain kernel, which ensures that if you are in the negative direction, this kernel is just 0. And you can do it if you, so if there are n minus negative directions, you should insert the simplest way to ensure the convergence is to insert a product of n differences of signs. And you can impose certain conditions on these vectors vi so that it does the job. So it ensures the convergence. At this point, you can ask what is the, what is important is that in contrast to the usual theta series, this guy is not modular, precisely because of the presence of these sign functions. Actually, it's a typical example of a high depth or depth n-1 mock modular form. At this point, you can ask what is the modular completion of this guy, and actually completion is constructed so there is a trivial recipe for this. You just expand this product, you pick up one term, which is given by product of n signs, and you replace it by the so-called generalized error functions. And you see, the argument depends on tau 2. This is why this guy is non-holomorphic. And you remember I mentioned that these guys appears in the expression for these coefficients R. And it is this reason why it's natural to construct solutions of this problem, in terms of indefinite theta series. So let me show how this works for n equal 2, the most trivial case, so 2 charges. So this is my equation. So R is essentially error function. This E1 is just the usual error function, minus sign. And so to have a modular function, well, you know, we just should have a theta series in terms of E1, no signs. What does it mean? It means that we should take G, which cancels this sign. So just take indefinite theta series, the same factor as here, and put sign so that in the sum they cancel. But this doesn't work because this guy is divergent. You need to have a second sign for convergence. But if you have second sign implies that in the completion should involve second error function, which we do not have. So what to do? And it turns out that for one particular choice of this vector W, you do not need to introduce error function. Namely, if this W is a null vector. Because you see, there is a norm here in the argument, and if it's 0, the argument goes to infinity, and when it does, the error function reduces just to the sign. Therefore, this is the ansatz for the solution, but the problem, you need to have a null vector. And in our case, well, in this particular case, n equal to 2, the lattice is just one-dimensional. Of course, it doesn't have any null vectors. So what to do? Well, the idea is kind of, well, it's a, one could say, standard trick in the theory of mock modular forms. You multiply by a Jacobi theta function, which effectively extend your lattice, adds additional directions. And in the case of n charges, so you start from negative definite lattice of this dimension, n-1, and ended up like with the already big in lattice of indefinite signature. Okay, just one more minute. So then you should also, this is not actually enough to find solution. You should also add the so-called refinement, so that you upgrade the functions to mock Jacobi forms. There are 2 reasons for that. This simplifies our coefficients, which determine the anomaly, and also this regularizes certain divergences appearing due to the null vectors. But the result is that some poles appear in the unrefined limit where you take this refined parameter to 0. And finally, the results, so what do we want? Now we want to find mock Jacobi forms on this extended lattice, which I mentioned, and then take the unrefined limit. And I claim that the solution to this problem is, well, can be explicitly written. So it's some combination of theta series and certain Jacobi forms, which are needed to cancel those poles, which I mentioned on the previous slide, just because we need a function which has a smooth limit at z equals 0. But these guys can be just written in terms of Jacobi theta series. And then the most non-trivial step is to evaluate analytically this unrefined limit. Well, again, probably numerically it's not a problem, but analytically it's very cumbersome. And we did it explicitly for arbitrary 2 and 3 charges. So this is our current situation of solution of the modular anomaly. So let me just conclude. So the main message which I told you is that we have developed an approach based on modularity, wall crossing, and direct integration of topological string, which allows to compute infinitely many a new topological invariance for compact Calabi-Yau threefolds. This program has been realized for one modulus Calabi-Yaus, and in particular for D4-branch charge R equal 1 or R equal 2. The first case is modular, the other one is mock modular. And this already produced new boundary conditions for the direct integration method, which allow us to bypass its limitations. And we also found the solutions of modular anomaly for higher charges. And so that this reduces the whole problem of finding generating functions to just finding a finite number of terms. And possible extensions, well, of course, there are many. Well, first of all, it would be nice to find polar terms for the remaining cases which we didn't for one modulus. But probably since here already we do not have enough knowledge of GV invariance, so and we already reached the maximal genus for most of Calabi-Yaus, probably we need some new strategy. And the hope is that there should exist some new strategy. So roughly speaking, using other wall crossing formulas to do the same trick. And I told you that we did it for one modulus Calabi-Yau, but exactly the same strategy works for any number of moduli, and the solutions will be, well, essentially the same. And also one can consider some particular cases like elliptic or K3 fibration, and this may introduce some additional structures and something interesting may appear. So let me just stop at this point and thank you for your attention. Well, no, that's the point. So we do not need a unique solution. It's enough to find any solution, any particular solution, and then the problem reduces to fixing the modular ambiguity. But this is the problem of finding polar terms, which we postpone. This is our second step, which we haven't done. Yeah, absolutely. Yeah. About S duality. It's here. You mean here? Well, it's just standard S duality of type 2B string theory. Sorry, can you repeat? Well, I'm not sure you see it directly here. Well, yeah, but you don't, because here my main object is this modular space M, and you don't see it. So what you want, don't see it there. Yeah, but it's the same. The point is that you get the same space either here or here. It is the same, exactly. No, unfortunately, the strategy, no, this wouldn't work. Because as I mentioned, under S duality, D6 branes go to NS5 branes. And we do not know NS5 brane corrections, which means that you cannot use it as a restriction on, let's say, BPS indices for D6 branes. You use it as a tool to derive NS5 brane corrections. Yeah, so if you can derive independently NS5 branes, then maybe one can extract some corrections. But now, yeah, it doesn't work like this. Yeah, but how does it help? Yeah. Well, any insight on how to find NS5 brane corrections is very welcome. So if you can tell me, suggest something, because this is really the, yeah, the, yeah. But just to tell you, the current status of the problem of finding the exact metric here is precisely we kind of know all the brane corrections, and what is missing are NS5 brane corrections. Even those we kind of determined for NS5 brane charge equal 1, roughly speaking, for one instant on effects, but the problem appears at multi-instantons. We do not understand multi-instantons. So there is something special about them, and yeah, any insight will be very welcome. So it's an old problem which stays for many, many years. And, yeah. Yeah. Well, on if okay, on this side, yeah, it's easy to tell for me what it is because it's just axiodilaton. Just one of the well, one of the fields appearing. Here, of course, it's also just the field which is just dual to the axiodilaton, but well, it's a little bit more complicated to explain. But, no, it is. It's one of the coordinates there. Well, yeah, yes.